In tonight's journey, we are going to examine people's most loved aircraft model, the Airbus A380. It weighs 575 tons, carries 500 people, and travels at 900 kilometers per hour through air 12 kilometers above the ground. And the cabin inside is quieter than most offices. Tonight, we go slowly through the most extraordinary flying machine ever built. There is a particular stillness that belongs to the upper deck of an Airbus A380 at cruise altitude, and if you have ever sat there for more than an hour, you know exactly what it is. The aircraft weighs more than 500,000 kilograms. It is burning through jet fuel at a rate that would empty a swimming pool in minutes. 4 of the largest turbofan engines ever put on a commercial aircraft are running at around 80% power somewhere beneath and behind you. And yet, the cabin around you is quieter than a library reading room. The seat beneath you carries almost no vibration. This is not normal. This is designed. The first thing that separates the A380 from almost every other commercial aircraft you will ever fly is the air itself. Most commercial jets maintain a cabin pressure equivalent to approximately 8,000 feet above sea level. At that altitude, the air has measurably less oxygen than at sea level. Blood oxygen saturation drops. Over the course of a long flight, the body works harder to extract what it needs from each breath, and the result accumulates as fatigue. Passengers on long-haul flights often arrive exhausted, partly because of where they have effectively been breathing for 16 hours. The A380 pressurizes its cabin to the equivalent of approximately 5,000 feet above sea level. The specification, confirmed by Airbus, is 1,520 meters, which is just under 5,000 feet. The difference from 8,000 feet is not dramatic in isolation, but across a flight of 14 or 16 hours, the body registers it. The air feels easier to breathe. The heaviness that normally settles in the head and behind the eyes on a long-haul flight is reduced. Passengers and crew who fly the A380 regularly describe arriving at their destination less depleted than they feel after equivalent flights on other aircraft. The aircraft is not doing anything miraculous. It is simply maintaining a pressure that the human body was built for, rather than the lower pressure that manufacturing limitations forced onto earlier generations of jets. The cabin of the A380 also produces approximately 50% less noise than the Boeing 747-400 it was designed to replace. This comes from several sources, all of them engineered. The acoustic insulation installed between the fuselage skin and the inner cabin lining, the design of the engines, and the simple physical advantage of a wider fuselage that allows more material between the outside of the aircraft and the person sitting inside it. The result is a background hum in the A380 cabin that sits below the threshold at which the nervous system begins treating sound as something requiring a response. You hear the aircraft. You do not feel pressured by it. The lighting above you during a night flight on the A380 shifts through a program coordinated by the airline. Midway through a long flight, the LED ceiling panels typically move through deep blues and soft violets, frequencies that the body associates with low light and rest. This is not decorative. It is circadian biology applied to an aluminium tube moving at Mach 0.85 above the Pacific Ocean. The aircraft is managing your body clock from the outside. None of this happened because someone at Airbus decided a quieter, more comfortable aircraft would be pleasant. It happened because a consortium of engineers across 5 countries spent years solving specific problems in specific ways. And the accumulated answers are what you feel when you sit in the upper deck at cruise, close your eyes, and realize that something this large should not be this still. Over the next chapters, we will follow how it was built, where it came from, and what it quietly changed about the world. If this is the kind of story that helps you rest, subscribe to Simple Science so the next one finds you. Leave a comment below telling us where in the world you are watching from and what time it is there. We love knowing. The experience described in the first chapter did not emerge from a single company's ambition. It emerged from a political agreement between nations that had been losing a commercial war for decades. By the mid-1960s, Boeing dominated global aviation. European aircraft manufacturers, working separately in the UK, France, Germany, and other countries, could not individually match Boeing's scale, its capital, or its production capacity. Each country's manufacturer was too small to develop a new wide-body jet alone. Together, they might be different. In 1970, Airbus industry was formally established as a European consortium, initially involving France and Germany, with the UK joining through Hawker Siddeley's wingwork. It was not a single company in the traditional sense. It was an agreement to act as one. Through the 1970s and 1980s, Airbus established itself with the A300 and then the A310 aircraft that competed credibly with Boeing and McDonnell Douglas on short and medium-haul routes. By the early 1990s, Airbus had earned roughly a third of the global commercial aircraft market. But the long-haul market was still dominated by one aircraft above all others, the Boeing 747, introduced in 1969, which had carried more long-haul passengers than any other jet in history. Airbus engineers began studying whether a larger aircraft was feasible as early as 1988, running internal research under the designation A380. The concept went through dozens of configurations: high-capacity single-deck layouts, twin-deck arrangements, blended wing bodies. By the mid-1990s, the direction was settled. A full double-deck aircraft, larger than the 747, designed to carry more passengers at lower cost per seat on the world's busiest long-haul routes. The A3XX project became a public proposal in 1994. The airline's Airbus needed to commit to the program as launch customers were cautious. The aircraft would require a new final assembly facility, new manufacturing plants across multiple countries, and a development effort that would take years before the first aircraft flew. The risk was significant. On December 19th, 2000, after securing commitments from several major airlines, Airbus formally launched the A380 program with a budget of 9.5 billion euros. It was the largest single investment ever made in commercial aviation at that time. The manufacturing arrangement that followed reflected the consortium's structure. Airbus UK, based in Broughton, North Wales, would build the wings. Airbus Germany in Hamburg would build forward and rear fuselage sections. Airbus France in Saint-Nazaire would build the centre fuselage and the wing centre box. Airbus Spain in Puerto Real, near Cadiz, would build the horizontal tailplane and tail cone. Final assembly would happen in Toulouse. What this meant in practice was that an aircraft would be designed and manufactured simultaneously across 4 countries, in 4 languages, in facilities that had never before needed to coordinate at this level. The engineering challenge was aeronautical. The organizational challenge was equally serious. Each country's section had to fit every other country's section to tolerances measured in millimeters. Wiring designed in France had to connect cleanly with wiring loomed in Germany. Systems specified in Toulouse had to function correctly when installed by engineers in Hamburg. The wiring problem, in the end, was what caused the first major crisis. Each A380 contains approximately 530 kilometres of electrical wiring, 98,000 individual wires, and 40,000 connectors. The design tools used in France and Germany for the wiring schematics were different versions of the same software, and they were not fully compatible. When the first fuselage sections were mated in Toulouse, the wiring did not fit as designed. The correction took months. The A380 program was delayed by nearly 2 years, and the development cost nearly doubled before the first aircraft flew. The people watching from inside the program described the period between 2005 and 2007, when the delays became public and the costs escalated, as one of genuine uncertainty about whether the aircraft would survive at all. It did, and the story of how its parts got from 4 countries to a single runway in southern France begins with a journey most of those passengers would never know happened. Before the Airbus A380 could be assembled in Toulouse, its components had to get there. The wings, built in Broughton in North Wales, were the most difficult to move. Each wing is 36.3 metres long and several metres wide at its widest point. Nothing in the standard freight network could carry them. Airbus had to invent a logistics chain from scratch. The wings leave Broughton by road to the port of Mostyn on the Welsh coast, where they are loaded onto a specially designed roll-on roll-off vessel called the Ville de Bordeaux. The ship crosses the English Channel and the Bay of Biscay to the port of Bordeaux in southwest France. From Bordeaux, the wings and other large fuselage sections arriving by sea are transferred to flat-bottomed barges and travel up the Garonne River inland to a small town called Langon. This river journey takes approximately 12 hours at low speed, the barge moving under bridges with barely a metre of clearance above the load. At Langon, the A380 components are lifted off the barges and placed onto purpose-built road transporters. The journey from Langon to the Toulouse final assembly facility is approximately 240 kilometres by road, and it is a road journey that cannot happen in daylight. The convoy exceptional travels at night, typically departing after 10 p.m. and arriving before 6 a.m. The load is too wide, too tall, and too long for normal road traffic. Where the route passes through towns and villages, the local road infrastructure had to be physically modified to accommodate the convoy. Some roundabouts along the designated route, which Airbus calls the route d'Airbus, were removed entirely and replaced with flat junctions. Road surfaces were reinforced. Street furniture was repositioned. Overhead cables were temporarily rerouted on the nights the convoy passed. The transporter moves at approximately 10 to 15 kilometers per hour. A full convoy includes the load, multiple escort vehicles, and a team of road managers coordinating with local authorities in real time. The route passes through the outskirts of towns. past farmhouses and small commercial premises, through the kind of French countryside that has been essentially unchanged for generations. And people come out to watch. In the towns along the route, residents who know the convoy schedule stand at the roadside at midnight or 1 a.m. to see an A380 wing pass through their village. The wing is so large that it does not look like a component in transit. It looks like something geological moving, a structure from a different scale of the world passing through a human one. Photographs from these nights show the wing flanked by the narrow facades of French country buildings, the road transport lights casting long shadows, the whole scene having a quality of the surreal that no still image fully captures. The convoy has run for every A380 ever assembled. Across the program's production of 251 aircraft, this logistics chain was repeated hundreds of times. The Ville de Bordeaux, the barges on the Garonne, the night convoys through sleeping villages, all of them part of a routine that most of the people who eventually sat in the finished aircraft never knew existed. The journey from Broughton to Toulouse takes approximately 1 week when conditions are good. The river and sea portions are weather dependent. In winter, the Garonne can run high, and barge clearances under bridges become a calculation that must be made in real time. In summer, the river can run low enough that cargo weight must be reduced. The logistics team has to plan each movement months in advance and remain ready to adapt. What arrives in Toulouse at the end of this chain is not yet an aircraft. It is a wing, a fuselage section, a tail component, each one built to tolerances of millimeters, each one requiring final fitting work that can only happen when all the other sections from Germany, France, and Spain have also completed their journeys and arrived at the same address. The wings that make that journey are worth understanding on their own, because what they are made of and what they do in flight is where the engineering becomes something that borders on the beautiful. The A380's wings are built at the Airbus UK facility in Broughton, a small town in Flintshire, North Wales, that has been making aircraft wings since the Second World War. The plant employs thousands of people and covers several hundred acres. Its primary output for over 15 years was the wing that made the world's largest passenger aircraft possible. Each A380 wing is 36.3 meters long, measured from root to tip. The full wingspan of the assembled aircraft is 79.75 meters, wider than the aircraft is long. Standing beneath a wing at an airport gate, the scale is difficult to absorb. The tip of the wing is further from you than most houses are wide. The upper surface of the A380 wing is made largely from carbon fiber reinforced polymer, a composite material that combines carbon fiber threads with a binding resin to produce a panel that is lighter than aluminium for its strength and stiffer under the compressive loads that a wing's upper surface experiences during flight. The lower surface, which experiences tension rather than compression, uses more conventional aluminium alloy. The choice of material at each location on the wing is an engineering decision about which properties matter most at that specific point. Carbon fiber allowed Airbus engineers to design an upper wing surface that carries the loads of flight while weighing significantly less than an equivalent aluminium structure would. That weight saving contributes directly to the aircraft's range and fuel efficiency. The wing also contains fuel tanks. Fuel is stored across multiple cells inside the wing structure, and the wing's internal volume is shaped in part by the need to carry that fuel. At maximum fuel load, the A380's wings hold the majority of the aircraft's total fuel capacity of approximately 320,000 litres. In flight, the wings do something that surprises passengers who notice it for the first time. They flex. Under the loads of cruise flight at maximum weight, the wingtips rise from their ground position by several meters. Airbus test data and engineering documentation indicate the wingtips can flex upward by approximately 3 to 4 meters compared to their resting position on the ground. From inside the upper deck cabin, passengers sitting near the trailing edge can sometimes see this movement during turbulence. The tip rising and falling in a slow arc that corresponds to the gusts passing through the wing. This flexibility is deliberate. A rigid wing transfers the full force of turbulence directly into the fuselage and the passengers. A wing designed to flex absorbs that energy, distributing and softening it across the span before what remains reaches the cabin. The material properties of the carbon fiber upper skin, combined with the overall structural design of the wing, produce a component that bends under load and returns to its original geometry thousands of times over the aircraft's service life. The wing's leading edge, the front surface that meets the oncoming air, incorporates slats that extend during takeoff and landing to increase the wing's effective area and curve, generating additional lift at lower speeds. The trailing edge carries flaps for the same purpose, and ailerons for roll control. All of these surfaces are driven by hydraulic actuators receiving commands from the fly-by-wire flight control computers. The engineers who designed this wing were working against several constraints simultaneously. It had to generate enough lift to get 575 tons airborne. It had to fit within the wingspan limits set by airport gate standards at the time, which constrained the maximum span. It had to be light enough that its own weight did not eliminate the advantage of its efficiency. And it had to be manufacturable, which, in the context of this wing, meant manufacturable in North Wales, and then shippable to France by sea and river. The wing arrives in Toulouse, having already completed one of the more unusual journeys in modern manufacturing. What happens when it gets there, and the forces that allow it to keep 575 tons in the air, begins with what is attached to its underside. The Airbus A380 is powered by 4 Rolls-Royce Trent 970 engines, one mounted under each wing. Each engine produces approximately 340 kilonewtons of thrust, enough to accelerate the aircraft to take off speed, and then climb it to cruise altitude with a full passenger load and a full fuel load aboard. 4 of them working together produce a combined thrust that, if applied to a family car, would accelerate it to highway speed in a fraction of a second. The Trent 970 is a high-bypass turbofan engine. To understand why that matters for the A380's unusual quietness, it helps to understand what high bypass means. A turbofan engine draws air in through a large fan at the front. Some of that air enters the combustion core, where it is mixed with fuel, ignited, and expelled at high temperature and velocity to generate thrust. But in a high bypass turbofan, the majority of the incoming air bypasses the combustion core entirely. It flows around the outside of the core in a cold stream, accelerated by the fan, and exits at the rear as a large, relatively slow-moving mass of air. The bypass ratio describes the proportion of air that takes this outer path relative to the air that enters the core. In the Trent 970, the bypass ratio is approximately 8.7 to 1. For every kilogram of air that enters the combustion core, approximately 8.7 kilograms bypass it. This architecture is why the engine is quiet. The noise of a jet engine comes primarily from the shear between the fast-moving exhaust gases and the surrounding slower air. A high bypass engine reduces this shear in two ways. First, the bypass air leaving the rear of the engine is moving at a lower velocity than combustion exhaust. Second, the bypass air wraps around the core exhaust, creating a buffer layer between the hottest, fastest gases and the open air. The result is a significant reduction in the noise produced per unit of thrust. The Trent 970 generates its thrust more efficiently and more quietly than the earlier generation engines that powered the Boeing 747 variants. The A380 was designed to replace. The combined effect of 4 high bypass engines and an aerodynamically clean airframe gives the A380 a ground noise footprint approximately 50% smaller than the 747-400. A community that lies under the approach path of an airport where the A380 has replaced the 747 on a given route is exposed to a meaningfully quieter aircraft. Inside the cabin, the effect of the engines is further removed by the aircraft's size. The fuselage of the A380 is large enough that significant sound-deadening insulation can be installed between the outer structure and the inner cabin lining without consuming space that would otherwise be available to passengers. The engines are further from the cabin walls than in a narrower aircraft. Distance reduces sound naturally. The insulation reduces it further. The fan at the front of each Trent 970 is approximately 3 meters in diameter. It rotates at several thousand revolutions per minute during cruise, and the tips of its blades travel at speeds approaching the speed of sound. This generates a characteristic tone, the low, steady note of a turbofan engine at cruise, which passengers in the A380 cabin hear as a deep, even hum, rather than as the higher frequency mechanical noise of older engine designs. The 4 engines together consume approximately 12 tons of fuel per hour during cruise at a typical range conditions. They are maintained on a cycle that involves regular inspections, bore scope checks of internal components, and periodic removal for deep overhaul. The Trent 970 is certified for operation on extended range twin-engine operations. Although the A380 is a quad-engine aircraft, and that certification applies to its components rather than the aircraft configuration. The engines generate the movement, but something more fundamental keeps 575 tons suspended between them. And the explanation for that belongs to the shape of the wing itself. Lift is one of the more misunderstood forces in everyday physics. The most common explanation, that air moves faster over a curved wing and therefore produces lower pressure above the wing than below it, is correct as far as it goes. But it is incomplete. What keeps 575 tons in the air involves aerodynamic forces operating across a vast surface, at high speed, and managed continuously throughout every flight. The A380's wings have a reference area of approximately 845 square meters. This is the total planform area of the wing viewed from above, and it is one of the largest of any commercial aircraft ever built. The relationship between this area, the aircraft's weight, and the speed at which it flies determines something called wing loading, the amount of lift the wing must generate per unit of area. For the A380 at maximum takeoff weight, the wing loading is approximately 663 kilograms per square meter. To generate the lift required to carry that load, the wing moves through the air at the right speed and at the right angle. At takeoff, the aircraft is moving at approximately 290 kilometers per hour. The leading edge slats and trailing edge flaps are extended, increasing the wing's effective area and curvature, and generating the additional lift that the lower speed requires. As the aircraft climbs and accelerates, the slats and flaps retract, and the clean wing takes over. At cruise, the A380 travels at approximately Mach 0.85, which is about 900 kilometers per hour at altitude. The wing's aerofoil cross-section, carefully designed and refined across years of wind tunnel testing and computational fluid dynamics simulation, generates a pressure difference between the upper and lower surfaces that produces the upward force needed to sustain cruise flight. This force must exactly balance the weight of the aircraft, which is decreasing as fuel burns. As fuel burns and the aircraft grows lighter, the pilots and the flight management computer manage something called step climb. Rather than maintaining a fixed altitude throughout a long flight, the aircraft climbs in stages as it lightens. At the start of a 14-hour flight, the A380 might cruise at 35,000 feet. Several hours later, lighter by 50 or more tons of burned fuel, it climbs to 37,000 feet, then 39,000 feet as the journey continues. At each higher altitude, the air is thinner and drag is lower, which improves fuel efficiency at the reduced weight. The physics of this management are calculated by computers operating continuously, but the underlying principle is simple. A lighter aircraft needs less fuel to maintain speed, and flying higher reduces the drag that consumes that fuel. The A380 is consuming itself slowly and using the reduction in its own weight to improve its efficiency as it goes. From a window seat during a long flight, the most visible evidence of all this aerodynamic work is the wing itself, the leading edge, smooth and sharp, parting the air, the upper surface slightly curved, ending in the long trailing edge from which the wake of disturbed air flows back and away. In clear air at cruise altitude, the view from the upper deck window shows a wing that is barely moving relative to the passenger. It is doing enormous work and showing almost none of it. At the wingtip, a curved vertical surface called a winglet redirects the airflow that would otherwise curl around the tip from high pressure below to low pressure above. This tip vortex, without the winglet, wastes energy and generates drag. The winglet recovers some of that energy, improving fuel efficiency by a measurable percentage across the life of the aircraft. The engineering of the A380 wing is the accumulation of decades of aerodynamic research, and it allows an aircraft of this size to fly with an efficiency measured in litres of fuel per passenger per 100 kilometres that compares favourably with a medium-sized car on a motorway. Inside that aircraft, above those wings, is a space that no previous commercial jet had been large enough to provide. Every commercial jet before the A380 had its passenger cabin on a single deck. The Boeing 747 introduced a partial upper deck in 1969. A short hump above the forward fuselage that seated a few dozen passengers. It became one of the 747's most recognizable features, but it was not a full second floor. The A380 is. Its upper deck runs the entire length of the fuselage, from the nose to the tail, giving the aircraft 2 complete floors of passenger space with no interruption. The combined usable floor space across both decks is 550 square meters. For comparison, the Boeing 747-8, the next largest commercial passenger aircraft, offers approximately 40% less usable floor space. An A380 in a typical 3-class configuration seats around 525 passengers. In a fully economy configuration, the certified maximum is 853. No other commercial aircraft comes close to either number. The upper deck of the A380 is reached from the main deck by 2 stairways, one near the front of the aircraft and one near the rear. Airlines design the stairs differently depending on whether they want the transition to feel utilitarian or considered. Singapore Airlines A380 upper deck has a stairway that some passengers have described as resembling a hotel lobby. Emirates positions its upper deck bar area near the front stairway, so business and first-class passengers arrive at their floor passing through a social space rather than arriving directly at their seat. What the upper deck offers structurally is distance from the primary noise and vibration sources of the aircraft. The 4 engines are mounted under the wings, which attach to the lower portion of the fuselage. The main landing gear retracts into bays beneath the main deck. The upper deck sits above and behind most of the structural load paths that carry vibration from the wings and engines into the fuselage. The result is that upper deck passengers experience marginally less sensation of the mechanical work the aircraft is doing than those on the main deck directly. The windows on the upper deck are also positioned differently. On the main deck, the windows sit at roughly seated eye level, offering a view predominantly outward and slightly downward over the wing. On the upper deck, the windows are at a slightly higher effective position, and the geometry of the fuselage means passengers look out and down at a steeper angle, able to see more of the wing's upper surface, and, on a clear night, more of the ground far below. Airlines have allocated the upper deck in different ways depending on their product strategy. Most place first and business class there, using the smaller total floor area of the upper deck to create lower seat density and more premium space. Qantas and Emirates place their most expensive seats on the upper deck. Singapore Airlines has configured its A380 with its renowned suites product exclusively on the upper deck forward section. The main deck, wider and longer than the upper, handles the bulk of the passenger load in economy. Its width allows seating configurations of up to 10 abreast with 2 aisles. Seat width in a 10 abreast main deck economy row on the A380 is slightly wider than the equivalent 10 abreast configuration on the Boeing 747-400, a difference passengers do notice over the course of a 14-hour flight. The experience of the 2 floors together is unlike any other commercial aircraft. Boarding at a large hub airport, 2 jet bridges often connect to the aircraft simultaneously, one at each deck. Passengers on a full A380 board quickly for an aircraft of this size, because the 2 entrances allow the flow to split immediately. The aircraft fills from both decks at once, and within a short time, 500 people have found their seats, settled their bags, and the doors are closed. What happens next, from the moment the flight deck prepares for pushback to the moment the aircraft leaves the ground, involves a control system that does not work like any aircraft most passengers have experienced before. In a conventional aircraft, control cables and hydraulic rods run from the cockpit to the control surfaces on the wings and tail. When the pilot pulls back on the control column, a physical connection transmits that movement to the elevators, which rise and pitch the nose upward. The pilot and the aircraft are mechanically linked. What the pilot does, the aircraft does. The A380 has no such cables. The pilots sit at side stick controllers, small joystick-like devices to the left of each seat. And when they move these controllers, the input is converted into an electrical signal. That signal travels to a set of flight control computers, which interpret the command, apply a set of rules called control laws, and then send instructions to the hydraulic actuators that physically move the control surfaces. Between the pilot's hand and the wing's response, there is always a computer. This system is called fly-by-wire, and Airbus has used it across its commercial aircraft family since the A320 entered service in 1988. On the A380, the architecture is more complex than on any previous Airbus, involving multiple redundant computers that cross-check each other's outputs. If one computer produces a result inconsistent with the others, it is overruled. The system is designed to continue operating correctly, even if multiple computers fail simultaneously. The most significant feature of fly-by-wire for passengers is the one they never experience directly: envelope protection. The flight control computers maintain a set of limits beyond which the aircraft cannot be commanded to operate, regardless of what the pilot inputs. The A380 in normal operation will not bank beyond 67 degrees. If a pilot pushes the side stick fully in the roll direction and holds it there, the aircraft will roll to 67 degrees and hold. It will not roll further. The moment the pilot releases the side stick to neutral, the aircraft returns to wings level flight automatically. There is no equivalent to this in a cable-controlled aircraft, where an extreme input by the pilot produces an extreme output from the aircraft without limit. The angle at which the nose can be raised is also constrained. The flight control system will not allow the aircraft to be pitched to an angle where the wing loses its ability to generate lift, a condition called a stall. In a cable-controlled aircraft, the pilot must learn through training to feel and respond to the onset of a stall and act accordingly. In the A380, under normal fly-by-wire control laws, the stall cannot be commanded. These protections do not replace pilot skill, they complement it. The pilots flying the A380 are trained in aircraft performance, emergency procedures, and the management of systems failures as comprehensively as pilots on any other type. What the protections remove is the category of accident that occurs when a correctly intentioned input exceeds what the aircraft structure can withstand, or when spatial disorientation in IMC causes an unusual attitude to develop beyond recovery. The side stick controllers themselves contribute to the cabin experience in an indirect way. In a conventional cockpit with a central control column, the column is visible from the first-class seats immediately behind the flight deck on some aircraft configurations. It moves visibly during flight. In the A380's side-stick cockpit, the controls are at the side of each pilot's seat and not visible to passengers. The flight deck door remains closed throughout flight, but the compact, unobtrusive nature of the fly-by-wire controls is part of a broader design philosophy in which the interface between human intention and aircraft response has been made as small and clean as possible. The aircraft watches over itself. The computers check each other. The pilots fly an aircraft that will not let itself be pushed past the edge of what it can safely do. What the aircraft also manages with similar precision is what the passengers inside it breathe. The air outside the A380 at 12,000 meters is approximately -56 degrees Celsius and contains roughly a quarter of the oxygen available at sea level. None of it reaches the passengers directly. Every breath taken in the A380 cabin is air that the aircraft has processed and managed before delivering it to the people inside. The A380 draws a portion of its cabin air supply from the engines, a process called bleed air, where compressed air from the engine's compressor stages is tapped off before reaching the combustion chamber, cooled and conditioned, and fed into the pressurization system. This supply is mixed with filtered, recirculated cabin air and delivered to the cabin continuously throughout the flight. The recirculated portion passes through high-efficiency particulate air filters, the same filtration standard used in hospital operating theatres, before it re-enters the cabin. These filters capture particles down to 0.3 microns, removing bacteria and most viruses from the recirculated airstream. The cabin air is replaced approximately every 2 to 3 minutes during normal flight operations. The air you breathe at minute 5 of a flight has almost entirely turned over by minute 8. It does not sit and accumulate. It cycles. Cabin pressure in the A380 is maintained at the equivalent of approximately 5,000 feet above sea level, as established by the aircraft's pressurization specification. This is significantly lower than the 8,000 feet cabin altitude maintained by most older commercial aircraft. At 8,000 feet equivalent, blood oxygen saturation in a healthy adult typically falls by 3 to 4 percentage points compared to sea level. This is not dangerous, but over the course of a 16-hour flight, the physiological cost accumulates as fatigue, mild headache, and reduced cognitive sharpness. At 5,000 feet equivalent, the oxygen available in each breath is closer to what the body experiences at moderate altitude cities such as Denver or Mexico City, places where millions of people live and work without impairment. The body on an A380 flight is not managing a significant oxygen deficit. It is breathing in conditions it was built for. The cabin humidity is another factor that distinguishes the A380 experience from older aircraft. The fuselage of the A380 incorporates sections of carbon fiber reinforced polymer alongside conventional aluminium alloy structures. Carbon fiber does not corrode. This allows Airbus to design a pressurization and humidity management system that maintains slightly higher humidity levels in the cabin than older all-aluminium aircraft, whose fuselages required low humidity to prevent corrosion of the structure. Low humidity causes the well-known dryness of the eyes, throat, and skin that passengers on older jets experience on long flights. Higher humidity reduces all three. On a 16-hour flight, the difference in how the body arrives at the destination is partly explained by pressure and partly by humidity. Passengers who fly the same route on an A380 and then on an older aircraft on a different occasion consistently describe the A380 arrival as less depleted. even when they have slept for the same number of hours on both flights. The air management system runs without pause throughout the flight. Its work is invisible. The passenger sits in a cabin that feels comfortable without being able to explain precisely why, and the explanation is in the air around them, filtered, pressurized, conditioned, and delivered at a rate of several hundred cubic meters per hour to a sealed room moving at 900 kilometers per hour. The aircraft tends to the body through the air. It also tends to the body through something else, something the engineers and the airlines chose to install in the ceiling above every seat. The light in the cabin is not decoration. It is an intervention. The human body regulates its sleep and wake cycle largely through light exposure. In daylight, the eye's photoreceptors detect the blue wavelengths predominant in sunlight and signal the brain to suppress melatonin, the hormone that promotes sleep. As natural light fades toward evening and shifts toward warmer, redder tones, melatonin rises and the body begins preparing for rest. This system evolved over millions of years of living with the sun. It does not update itself automatically when placed inside a metal tube crossing 12 time zones in 16 hours. The engineers and designers who fitted the A380 with a full LED mood lighting system were working with this biology directly. Before the LED generation of cabin lighting, aircraft used fluorescent tubes producing a fixed white light that the airline could dim but not shift in color temperature. The light was either on or off, bright or less bright. The A380, from its earliest production versions, used LED systems that could produce thousands of color combinations. The ceiling panels, the sidewall lighting, the cabin ambient glow could all be programmed to shift gradually through hues and intensities across the arc of a flight. Airlines program their A380 lighting in coordination with their meal and service schedules, and increasingly with the science of circadian adjustment. A typical long-haul program begins at boarding with warm amber tones that signal welcome and comfort. As the aircraft climbs and initial meal service concludes, the cabin light remains relatively bright and social. Then, as the long sleep period of the flight approaches, the lighting shifts. The color temperature moves toward cool blue and violet, frequencies associated with low ambient light and the onset of evening. The intensity decreases. The cabin begins to look and feel like a room at dusk. This shift is not purely aesthetic. Blue and cool white light suppresses melatonin production. It keeps the nervous system alert. By reducing blue light and moving toward warmer, dimmer tones, the aircraft's lighting system allows melatonin to rise naturally in passengers who are trying to sleep during the flight, even when that sleep is occurring at a local time that bears no relationship to the time at the destination. In the hours before landing, the lighting program runs in the opposite direction. The cabin brightens gradually, beginning with a gentle increase in cool white components that mimics the early stages of sunrise. This is not a jarring transition. It takes place over 20 to 30 minutes, slowly raising the illumination in a way that nudges the body's alertness upward before the descent begins. Passengers who experience this well-managed sequence report waking from in-flight sleep less disoriented than they expect to be. Emirates has designed its A380 lighting program in detail, with phase transitions coordinated to specific routes and departure times. Singapore Airlines and Qantas have similar programs. The lighting is adjusted based on whether the flight is departing in the evening local time or the middle of the day, and whether the destination is east or west, because the direction of travel determines whether the body needs to advance or delay its clock. The science of this is circadian biology, a field with a substantial research base. The application of it to commercial aviation, specifically to the management of long-haul jet lag through carefully designed cabin-light environments, is one of the less visible but genuinely effective improvements that the A380 generation of aircraft introduced. On a 16-hour flight, the lighting program runs its entire arc once. By the time the aircraft begins its descent, the ceiling above the passengers has cycled from warm amber through deep cool blue and back again, guiding the body through a compressed artificial day, without most passengers being consciously aware that anything was managing them. The light was one part of the engineering of comfort inside this aircraft. The sound was another, and the work that went into reducing it reveals how seriously the designers of the A380 took the experience of rest at altitude. Measured from the ground directly under the approach path, the A380 produces approximately 50% less acoustic energy than the Boeing 747-400 it was designed to replace. This figure, confirmed by Airbus and verified in independent assessments conducted at airports, including London Heathrow, is not a marginal improvement. Half the noise means that communities under flight paths experience a genuinely different quality of night when the aircraft type changes. Inside the cabin, the same ambition drove the acoustic design. The A380's fuselage cross-section is significantly larger than any previous commercial aircraft, where the internal diameter of a Boeing 747 is approximately 6.1 meters. The A380's internal diameter is approximately 7.14 meters. This additional space between the outer fuselage skin and the inner cabin lining is not wasted. Acoustic engineers used it to install layers of sound-deadening material that a narrower aircraft simply could not accommodate without removing usable cabin volume. The treatment is applied at multiple layers. Between the fuselage frames and the outer skin, acoustic blankets absorb vibration from the structure. Between the frames and the inner cabin lining, secondary damping panels interrupt the path that sound would otherwise take from outside the aircraft into the cabin. The ceiling panels are designed with their own acoustic properties, absorbing rather than reflecting the sound that enters the cabin from above. The result is a cabin that is significantly quieter at cruise than any previous wide-body jet. The windows contribute to this as well. The A380's windows use a double-pane construction, with a gap between the panes that acts as an acoustic buffer. This is the same principle as double glazing in buildings, where the airspace between two panes of glass reduces the transmission of sound from outside to inside. Aircraft window vibration is one of the more significant noise paths into the cabin on older jets, and the A380's window design addresses it directly. At cruise altitude and speed, the dominant remaining noise sources in the A380 cabin are boundary layer turbulence over the fuselage surface, the low-frequency tones of the engines transmitted through the structure, and the ventilation system delivering conditioned air. All three are present in every commercial aircraft at altitude. In the A380, their combined level is lower than on aircraft, with thinner fuselages, fewer acoustic treatments, and less efficient engines. The difference is experienced as a quality of stillness rather than a specific absence. The A380 cabin is not silent. The background hum is there, but it sits below the threshold at which the brain begins interpreting sound as requiring attention. Sounds that register as signals, as inputs requiring a response, generate a background cognitive load that is present throughout a long flight and contributes to the exhaustion of arrival. The A380's cabin sound is below that threshold for most people. It registers as environment rather than signal. Airlines have also contributed to the acoustic environment through their choices of soft furnishings and cabin materials. Heavy carpeting, padded seatbacks, fabric-covered sidewalls, and ceiling panels all absorb sound within the cabin itself, preventing the reflections and reverberations that hard surfaces would create. The materials choices that make a premium cabin feel luxurious serve a functional acoustic purpose simultaneously. The combination of structural acoustic treatment, high bypass quiet engines, and carefully specified cabin materials produces an aircraft where a passenger sitting in a window seat at cruise, with no music playing and no other passengers speaking near them, hears approximately what a person would hear in an air-conditioned office building. A low, even background that the brain decides to stop tracking. In that acoustic environment, sustained by filtered air at a pressure the body finds manageable, and lit by a ceiling that is slowly adjusting toward the color temperature of dusk, sleep becomes easier than it has any right to be at 40,000 feet. The place that makes all of this possible was designed from the ground up for one purpose: to build the world's largest aircraft, once, and then again and again. The building that assembles the A380 is called the Jean-Luc Lagardère Final Assembly Line, and it was built specifically for this aircraft. Nothing existed before it that could accommodate what the A380 required. The hall is approximately 490 meters long, 250 meters wide, and 46 meters tall at its highest point. When the first sections arrived from Germany, France, Spain, and Wales, the building was waiting for them. Assembly begins with the fuselage. The forward and rear sections, built in Hamburg, are brought together with the center section, built in Saint-Nazaire, and mated to tolerances of millimeters. Engineers measure and adjust the alignment at every joint before the fasteners are driven. A misalignment that would be invisible to the eye could accumulate stresses across thousands of flight cycles that would eventually show up as fatigue cracking in the structure. The tolerances are specified because the consequences of ignoring them arrive years later and far from Toulouse. Once the fuselage sections are joined, the wing center box, built in Saint-Nazaire, is integrated. Then the wings arrive from their time in storage after the convoy exceptionnel, and the wing-to-fuselage mating takes place. This is one of the most precise operations in the assembly sequence. The wing must attach at exactly the correct angle, called the incidence angle, to generate the right lift characteristics in flight. A degree of error here cannot be corrected later without disassembling the aircraft. The engines are installed, the landing gear systems fitted, and then the wiring begins. Each A380 contains approximately 530 kilometers of electrical wiring. Laid end to end, the wiring from a single A380 would stretch from Toulouse to Hamburg, and most of the way back. There are 98,000 individual wires and 40,000 connectors. The wiring harnesses are pre-assembled in workshops and brought to the aircraft for installation. But the work of routing them through the aircraft structure, connecting them at each end, and testing every circuit is a task measured in weeks. The wiring was the problem that nearly broke the program in 2006. The design tools used by the teams in France and Germany had been different software versions, and the wiring schematics they produced were not compatible when the aircraft was physically assembled. Harnesses designed in one country did not fit correctly when installed in sections designed in the other. The corrections required extensive rework across multiple aircraft already in production. The delays and costs that followed brought the program to the edge of viability. After wiring, the aircraft receives its cabin interior. The seats, galleys, overhead bins, monuments, lavatories, and all soft furnishings are installed. The floor panels are fitted. The ceiling panels are installed. The windows are sealed. What arrived as joined metal sections progressively becomes the interior, that passengers will spend 16 hours inside. The first flight of each production, A380, takes place from Toulouse-Blagnac Airport. Each aircraft must demonstrate its airworthiness before delivery, flying a test program that verifies the installed systems, measures performance, and confirms that the aircraft meets its certified specifications. This maiden flight typically occurs several weeks before the delivery to the customer. The test pilots who fly each production, A380, are looking for anything that differs from the design baseline. A vibration on one flight surface, an anomalous reading from a system sensor, a cabin pressurization performance that does not match the model. Each finding is investigated, addressed, and verified before the aircraft is accepted. When the customer's acceptance flight is completed and the delivery documentation is signed, the aircraft is handed over and flown directly to the airline's maintenance base for final configuration, livery application, if not already complete, and crew familiarization before entering service. The process from the arrival of the first fuselage section in Toulouse to the delivery flight takes several months. During that time, the aircraft is touched by thousands of workers. It contains components made in 4 countries. It carries the accumulated engineering decisions of thousands of engineers who worked on its design over more than a decade. What some of those airlines then did with the space inside that aircraft was unlike anything that had existed at cruising altitude before. When Emirates took delivery of its first A380, the airline had already decided that the upper deck would contain something aviation had not produced before at commercial scale: a private room in the sky. Emirates A380 First Class consists of enclosed suites on the upper deck. Each suite has a full-height sliding door that closes to create a private space separated from the cabin and from other passengers. Inside is a seat that converts to a fully flat bed, a personal minibar, a vanity mirror, and a storage area. The suite is lined with polished wood trim and upholstered surfaces. The ceiling is close enough to touch. When the door is closed at cruise altitude and the lighting is adjusted, the space is quieter and more private than many hotel rooms. In 2017, Emirates introduced onboard shower spas on its A380. There are 2 of them, located at the front of the upper deck, each the size of a compact bathroom. Each spa provides up to 5 minutes of hot water per passenger on a given sector. The water is stored in tanks and heated on board. The concept had been considered impractical by most in the industry. Emirates built it anyway, and it has been in operation on its A380 fleet since. Singapore Airlines developed the A380 suites, its highest product class, exclusively for the upper deck of its A380 aircraft. Each suite is a private cabin with a sliding door, a full flat bed, a large monitor, and personal storage. In the aircraft's original configuration, adjacent suites could be opened to one another by lowering a partition, creating a shared space for two passengers travelling together. The double bed this produced was the first of its kind in commercial aviation. Korean Air, Qatar Airways, and Etihad Airways all installed onboard lounges on their A380s, accessible to business and first-class passengers. Qatar Airways' Q-Suite product, introduced on other aircraft, has its roots in a design philosophy the A380's space helped prove viable. The onboard bar on an Emirates A380 became one of the most photographed interiors in commercial aviation during the 2000s, visited by passengers who wanted to see for themselves whether something that visible in advertising could actually exist. None of this was incidental. The A380's volume made it possible. A Boeing 747-400 upper deck cabin is approximately 58 meters long, with a floor width of around 6 meters. The A380's upper deck is slightly narrower in usable floor width, but runs the full length of the aircraft, and its greater overall height allows cabin fittings that would be constrained in a shorter fuselage cross-section. Airlines designing premium products for the A380 had room that no previous commercial aircraft had given them. The bar areas and lounge spaces that Emirates and Korean Air installed on their A380s are not large rooms. They are spaces roughly the size of a domestic kitchen, but at 40,000 feet, moving at Mach 0.85, a domestic kitchen is a remarkable thing to find. Passengers who stand at the bar of an Emirates A380 on a night flight over the Arabian Gulf, holding a drink, looking out of the window at the darkness below, report a particular quality of unreality. They are simultaneously in one of the most ordinary domestic situations, and one of the most extraordinary physical ones. The aircraft made this contradiction possible by being large enough that the space for it existed. The engineers who designed the fuselage cross-section, the structural engineers who calculated the loads, the certification engineers who approved the cabin configuration, none of them were designing a bar. They were designing a structure that was large enough and strong enough to carry whatever an airline put inside it. What some airlines chose to put inside it was a private room, a shower, and somewhere to stand and look out a window at the planet below. The fuel that carries all of this through the sky is worth understanding on its own. The A380 carries up to approximately 320,000 litres of jet fuel at full capacity. This fuel is distributed across multiple tank cells, located inside the wings and in the horizontal tailplane. At maximum takeoff weight, fuel accounts for roughly a quarter of the total weight of the aircraft. The aircraft that lifts off a runway in Dubai, bound for Los Angeles, is, in one sense, mostly fuel. The structure, the engines, the passengers, the cargo, and the fuel itself combine to produce the 575-ton total. And of that, fuel represents a very large portion. As the flight progresses, the aircraft burns that fuel and becomes lighter. On a 16-hour sector, the A380 arrives at its destination, weighing substantially less than it did at departure. More than 100 tons of fuel have been converted into energy, thrust, and heat, and the aircraft has consumed itself, in the most literal sense, to complete the journey. The management of this fuel is continuous and precise. The fuel is not drawn from the tanks in a fixed sequence. The flight management system and the fuel management system work together to draw fuel in a pattern that maintains the aircraft's center of gravity within the required range as weight changes. If fuel were drawn only from the wing tanks, for example, the wing bending relief that fuel provides, fuel in the wings reduces the upward bending moment that lift imposes on the wing root, would be lost prematurely. If fuel were drawn unevenly, the aircraft would develop an imbalance that the flight control system would have to work to correct, wasting energy in the process. The horizontal tailplane tank serves a specific function. Fuel transferred into or out of the tail tank shifts the aircraft's center of gravity aft or forward. This is used deliberately to adjust the trim of the aircraft, reducing the load on the horizontal tail and thereby reducing drag. A tail-heavy aircraft requires less downforce from the horizontal stabilizer to maintain level flight, which is more efficient. The fuel system is an efficiency tool as much as an energy store. The fuel consumption of the A380, calculated per passenger on a fully loaded aircraft, works out to approximately 3 litres per 100 kilometres. This figure is cited regularly in Airbus marketing materials and has been independently verified by various aviation analysts. For comparison, it is roughly equivalent to a modern mid-size car carrying 4 passengers. That a 575-ton aircraft moving at 900 kilometers per hour over 14,000 kilometers achieves this efficiency is the result of every aerodynamic and engineering decision described across the previous chapters working together. The high bypass engines, the clean aerodynamic form, the light composite structures, the precision of fly-by-wire control minimizing wasted control surface deflection. The fuel also generates a visible effect that passengers near the rear of the aircraft can sometimes observe during fuel dump procedures, which are rare, or more commonly when watching the wing trailing edge in certain conditions. Fuel venting, condensation trails from the fuel mass in the cold upper atmosphere, and the rippling heat haze at the engine exhaust on startup are all visible reminders that this aircraft is a combustion system of extraordinary scale. Before each long-haul departure, the refueling process itself takes time. At maximum fuel load, the A380 is receiving fuel through multiple refueling points simultaneously, with ground equipment managing the flow to achieve the precise distribution the flight plan requires. The fueling crew works from a manifest that specifies exactly how many litres go into each tank cell, in which sequence, to achieve the target weight and balance for that specific flight with that specific payload. Every detail of the fuel load is calculated before the pilots take their seats. The people in those seats are responsible for managing everything from that moment, including the events that nobody plans for. 2 pilots fly every A380. They sit in a wide flight deck above the main passenger deck, separated from the cabin by a reinforced door that remains locked throughout the flight. Between them, the instruments of one of the most complex civil aircraft ever certified display the state of the aircraft in more detail than any previous generation of cockpit. The fly-by-wire side-stick controllers sit at the outer edge of each pilot's seat. The thrust levers for 4 engines are in the center console between them. Both pilots hold an A380 type rating, a qualification specific to this aircraft, obtained through months of training on ground-based simulators and in the air. The type rating covers the aircraft system's architecture, its performance envelope, its normal procedures, and its abnormal and emergency procedures. The A380 has more systems, more redundancy, and more potential failure combinations than any previous Airbus aircraft, and the training reflects this. On November 4th, 2010, a Qantas A380 operating as Flight QF32 from Singapore to Sydney demonstrated what those procedures were designed to manage. 4 minutes after departing Singapore Changi Airport, while climbing over Batam Island in Indonesia, the number 2 engine, the left inner engine, suffered an uncontained failure. The intermediate pressure turbine disc inside the Rolls-Royce Trent 970 engine fractured at high speed. Fragments of the disc were ejected through the engine casing at enormous velocity, penetrating the lower wing structure above the engine, severing hydraulic lines, damaging fuel tanks, cutting electrical cables, and destroying or disabling multiple flight control system components. The flight deck received alerts for dozens of system failures in rapid succession. Hydraulic systems, fuel systems, flight control surfaces, engine management, braking systems. The system's display presented a cascade of warnings that the crew had to work through methodically, while simultaneously assessing whether the aircraft could be controlled. Captain Richard de Crespigny, First Officer Matt Hicks, and 3 additional Airbus qualified pilots who were occupying the flight deck for training purposes, worked through the failures for approximately 2 hours before landing the aircraft back at Singapore. The approach required managing an aircraft with degraded flight controls, limited braking capability, and fuel imbalance from the wing tank damage. The landing was heavy but successful. All 469 people on board were uninjured. The investigation that followed, conducted by the Australian Transport Safety Bureau, identified the specific manufacturing defect in an oil feed pipe within the engine that had led to the uncontained failure. Rolls-Royce addressed the fault. The QF32 aircraft was repaired over approximately 18 months at Singapore and returned to Qantas service. What the incident demonstrated about the A380's design was significant. The aircraft had sustained damage to multiple critical systems simultaneously and remained flyable. The structural redundancy in the wing had contained what was, by any engineering definition, a severe failure event. The hydraulic architecture, with its 4 independent circuits, had retained sufficient function for control. No fuel fire had developed despite the wing tank penetration. The A380 was not the cause of QF32. The cause was a manufacturing defect in a component of one of its engines. But the aircraft's response to the event, its capacity to absorb damage at that scale and return 469 people safely to the ground, was a demonstration of an engineering philosophy that had been incorporated into the design from the beginning, that a failure in one system must not cascade into a failure in all systems. Captain de Crespigny later wrote a book about the experience. The aircraft he landed that day, registered VHOQA and named Nancy Bird Walton after the pioneering Australian aviator, eventually returned to Qantas service and flew for several more years before being retired. The people who designed the aircraft this crew flew, the engineers who made the redundancy decisions that kept QF-32 in the air, were working toward a first flight that had already happened 5 years earlier. On April 27, 2005, the first Airbus A380 prototype, registration F-WWOW, lifted off from Toulouse-Blagnac Airport at 10:29 in the morning local time. At the controls were Airbus chief test pilot Jacques Rosay and his crew. The flight lasted 3 hours and 54 minutes. When the aircraft landed back at Toulouse, the 5,000 engineers and workers gathered on the airfield gave it a reception that eyewitnesses described as one of the most emotional moments in European industrial history. The program had been 5 years in development since the December 2000 launch, and several years of study and feasibility work before that. The aircraft had survived the wiring crisis that had pushed its schedule 2 years past the original target. It had survived the internal politics of a consortium, manufacturing in 4 countries with imperfect coordination, and it had flown. Jacques Rosay's post-flight assessment described the aircraft as flying exactly as the simulators predicted, which in aircraft testing is the highest possible affirmation of an engineering program's execution. The type certificate, certifying the A380 as airworthy for commercial operation, was awarded by the European Aviation Safety Agency and the US Federal Aviation Administration, jointly on December 12, 2006. This certification process had consumed thousands of flight test hours and ground test hours across the prototype fleet. On October 15, 2007, Singapore Airlines took delivery of the first production A380 at a ceremony in Toulouse. 10 days later, on October 25th, the airline operated Flight SQ380 from Singapore Changi Airport to Sydney Kingsford Smith Airport. The tickets for this first commercial service had been sold through a charity auction. They ranged in price from $560 to over $100,000, with all proceeds donated to charity, raising more than $1.2 million. Among the 455 passengers on board were individuals of 35 different nationalities. The youngest passenger was 10 months old. The oldest was 91. When SQ380 landed in Sydney that afternoon, it was met by hundreds of airport workers and aviation enthusiasts who had gathered along the perimeter fence to watch. A damp, overcast afternoon in Sydney did not reduce the size of the crowd. The aircraft that had left the Toulouse Assembly Hall as joined sections of metal from 4 countries had, in the space of 2 years, become operational in commercial service on one of the most significant intercontinental routes in the world. The flight time from Singapore to Sydney in that aircraft was approximately 7 hours and 20 minutes. The passengers on the inaugural service occupied a cabin that had never been available for commercial travel before, at a pressure altitude and noise level that distinguished it from anything in the previous generation of long-haul jets. Singapore Airlines went on to develop the A380 into its flagship aircraft for premium long-haul service, eventually introducing its acclaimed suites product and its business-class double beds exclusively on the type. The aircraft became associated in the public mind with a certain quality of long-haul travel that the airline industry had not consistently delivered before at this scale. Other airlines that took the A380 into service through the following years, including Emirates, Qantas, Lufthansa, British Airways, Air France, Korean Air, and others, Each adapted the platform to their own product strategies. But all of them inherited the same fundamental characteristics: the double deck, the quiet engines, the pressurized cabin at 5,000 feet equivalent, and the scale that allowed them to offer something the smaller aircraft around them could not. What the A380's arrival on busy routes also changed was something that passengers never directly experienced, but that the people living near the airports could measure on their own terms. London Heathrow is one of the world's busiest international airports, with flight paths that pass directly over densely populated areas of West London. For decades, the predominant long-haul aircraft using those paths was the Boeing 747-400. When airlines operating routes into Heathrow began replacing 747s with A380 OGs, the communities under those approaches experienced something that noise monitoring data subsequently confirmed: a measurable reduction in the sound reaching their homes. The A380 produces an acoustic footprint on the ground approximately 50% smaller than the 747-400. This means that on a standard noise contour map, where lines mark the geographic boundaries of exposure to noise above a given decibel level, the area enclosed within each contour shrinks when the aircraft type changes. Households that sat inside the 60 decibel contour of a 747-400 approach found themselves outside the equivalent contour on nights when an A380 was flying the same path at the same time. The scale of this change, at an airport processing hundreds of long-haul movements per day, is significant. The World Health Organization's Environmental Noise Guidelines, published in 2018, established links between chronic exposure to aircraft noise above certain thresholds and increased risk of cardiovascular disease, as well as cognitive impairment in children living near flight paths. Aircraft noise is not a quality of life issue in isolation. It is a public health issue with documented physiological consequences. The engineering decisions that made the A380 quieter were not made with these communities as the primary objective. They were made to reduce fuel burn, to produce a competitive product, to meet certification noise standards that had become increasingly stringent since the 1970s. The community noise benefit was a consequence rather than a goal, but it was real, and in the communities affected, it was felt. Night flights at Heathrow are restricted by a noise quota system. Under this system, each aircraft type is assigned a quota count based on its noise certification level. The A380 has a low quota count because of its certificated noise performance. An airline operating A380s can therefore fly more night movements within the same overall quota than an airline operating older, noisier aircraft. The economics of this system have contributed to the A380's adoption on routes where night arrivals and departures are commercially important. Emirates operates the largest A380 fleet of any airline, with well over 100 aircraft in service before the COVID period. Its primary hub, Dubai International Airport, handles A380 operations at high frequency throughout the day and night. The progressive replacement of older wide-body types with A380s on its long-haul network has produced a cumulative noise reduction over Dubai and its surroundings, and over every destination airport on its network, where the 747 or older wide-body type preceded the A380. The Qantas A380 fleet operates on routes including Sydney to Singapore, Sydney to Dubai, and Sydney to London via Dubai. The communities around Sydney Airport, which sits within close proximity to suburbs of one of Australia's largest cities, have seen noise monitoring data reflect the progressive replacement of older aircraft types with the A380 over the years since 2008. This is what a better engineered aircraft can do at scale. The benefit is not concentrated in the engineering achievement. It distributes across the geography of every route the aircraft flies, across every community, beneath every approach. On every night, the aircraft is in service. The aircraft moved through the air, and the air around the airports below it changed. Not dramatically, not overnight, but measurably. Every flight a quieter one than the flight it replaced. Every night slightly less loud than the night before. And then, in the spring of 2020, every A380 in the world stopped flying. In March 2020, aviation collapsed. Not gradually, not in stages, but within the space of 2 weeks as borders closed across every continent. Airlines went from full schedules to near-zero operations faster than any planning scenario had anticipated. The aircraft that filled the world's long-haul routes had nowhere to go. The A380, with its high capacity and high operating cost, was among the first types to be grounded in large numbers. An aircraft designed to carry 500 people efficiently at full load becomes deeply uneconomic at low load. With passenger numbers reduced to a fraction of normal, most A380 operators had no commercially rational reason to fly the type. They parked them. The aircraft needed somewhere dry, where low humidity would preserve the unpressurized systems, protect the rubber seals, and prevent corrosion from taking hold during an extended period on the ground. 3 locations became the primary repositories for the world's parked A380 fleet. Teruel Airport in eastern Spain, surrounded by the dry plateau of the Iberian interior, became the largest A380 storage site in Europe. The airport had operated as an aircraft maintenance and storage facility for years, and its runway and apron could accommodate the A380's size and weight. Aircraft arrived from airlines across Europe and were parked in rows. The sight of dozens of A380s from multiple airlines standing together on a regional Spanish airport apron, engines cocooned and cabins sealed, was unlike anything the aviation industry had previously produced as an image. Southern California Logistics Airport in Victorville, northeast of Los Angeles, provided storage capacity in a desert climate well suited to long-term preservation. A380s from Asian and Middle Eastern carriers were positioned there alongside aircraft of other types, turning the facility into a museum of temporarily suspended aviation. Alice Springs Airport in Central Australia, one of the driest inhabited places on Earth, received a portion of the Qantas A380 fleet. The aircraft were parked in the Australian desert and left to wait. At peak grounding in mid-2020, a significant portion of the entire global A380 fleet was simultaneously parked at these 3 locations. Airlines assessed whether they would ever return to service. Air France made the decision early. It would not. The airline's A380 fleet was permanently retired, the aircraft broken up for parts or put up for sale. Lufthansa reduced its A380 fleet substantially. Several smaller operators who had taken the aircraft into service announced they would not reactivate it. Emirates, the largest operator, went in the opposite direction. The airline committed to returning its A380 fleet to service as the global travel recovery began in 2021 and 2022. It was, from Emirates' perspective, the aircraft, its network, and its premium product had been built around, and no other aircraft could replace what the A380's capacity and two-class upper deck provided on its core routes. The return to service involved inspections, engine run-ups, systems checks, and flight tests for each individual aircraft after the extended storage. Aircraft that had been parked for 18 months required careful assessment of every system that had sat dormant through cycles of desert heat and cold. The images of A380s in the desert remain among the stranger documents of that period. Hundreds of examples of the most complex commercial aircraft ever built, sitting still in a straight line, their cabins empty and dark, the engines silent, an aircraft defined by movement, by the constant management of fuel and air and aerodynamic forces, reduced to an object waiting on a dry plateau for the world to decide what to do next. Most of them eventually flew again, and the last one ever built was delivered while some of them were still waiting. On February 14th, 2019, Airbus announced it would end A380 production. The decision followed Emirates' reduction of a large, outstanding order. Without the world's biggest A380 operator committing to sufficient new deliveries, the assembly line could not continue at an economically viable rate. The announcement was direct and offered no ambiguity. Production would wind down, and the last aircraft would be delivered in 2021. The A380 program had sold 251 aircraft in total across its production life. The original break-even estimate had required the sale of more than 400. Airbus had invested an estimated €25 billion in developing the aircraft, a figure that was never recovered from the program's revenues. The A380 was a financial loss for the company that built it. It was also an engineering achievement of a scale and ambition that is unlikely to be repeated. The aircraft that made the A380 program commercially difficult were not competitors in the traditional sense. They were twin-engine wide-bodies, the Airbus A350 and the Boeing 787 Dreamliner. These aircraft, using highly efficient high-bypass engines and composite structures, could fly routes of similar range to the A380, but with smaller capacity and lower fuel burn per trip. Airlines that had used the A380 on high-density routes could now operate the same route with a smaller aircraft more frequently, offering passengers more departure times without filling 500 seats to break even. The economics of the twin-aisle twin-engine jet made the four-engine double-decker harder to justify as a new order. On March 17th, 2021, manufacturing serial number 272, the final Airbus A380 ever to be produced, made its maiden flight from Toulouse-Blagnac Airport. It flew from Toulouse to Hamburg for cabin fitting and interior completion. On December 16th, 2021, it was delivered to Emirates, which had been the recipient of both the first and last production, A380. The aircraft's registration was a 6-EVS. The A380 program ended, as many ambitious industrial projects end, with the gap between what was achieved and what was required being too wide to bridge. What was achieved was the world's largest commercial passenger aircraft. Quieter than the aircraft it replaced, more comfortable for passengers on long routes, capable of generating passenger economics that justified its operation on the world's highest demand routes, and built from components manufactured across 4 European countries in an act of industrial cooperation that had not previously existed at that scale in commercial aviation. What was required was volume. The market did not provide it in the numbers the program needed. The 251 aircraft that were delivered are still flying. As of the end of production, the global A380 fleet had completed more than 800,000 flights over more than 7 million block hours, with no hull losses and no fatalities. This safety record, across more than a decade of operation on some of the world's busiest routes, is a separate achievement from the financial one. The passengers on those 800,000 flights were carried by an aircraft that did not announce its effort. The wings flexed above them. The engines ran at their steady bypass ratio. The air was filtered and delivered at a pressure their bodies found manageable. The light above them shifted with the hours. And most of them arrived less exhausted than they expected to be. The last one built is in Emirates service, flying the same routes its predecessors have flown since 2007. At some point tonight, it is at cruise altitude, somewhere above the globe, carrying several hundred people through air they cannot see and cannot survive without, toward a destination that is many hours away. They are almost certainly asleep. We started in the upper deck at cruise. Return there now. The engines are running at steady thrust. The cabin is lit in cool blue. The air has been filtered and delivered at a pressure the body finds natural. The wings, 36 meters each, are flexing slightly in the dark, outside the window, doing the continuous work of lift that keeps 575 tons aloft across an ocean or a continent, or the curved black surface of the night. Every detail of what surrounds those passengers was the product of a decision made by someone, somewhere, after a calculation or a test, or a failure that taught them something they applied here. The acoustic panels in the ceiling were specified by engineers who measured frequencies in a wind tunnel and determined which materials absorbed which wavelengths most efficiently. The LED lighting program, shifting slowly toward warmer tones, was designed by people who understood that melatonin is sensitive to color temperature and that a passenger, given the right light environment, sleeps more easily. The pressurization system, holding the cabin at 5,000 feet equivalent, was specified because someone calculated that the cost of maintaining higher pressure in this particular fuselage cross-section was worthwhile for the difference it made to how passengers felt upon arrival. The wings that carried the fuselage containing all of these systems were built in Broughton, Wales, and loaded onto a ship and taken by barge up a French river at night, and moved by road through sleeping villages at 10 kilometres per hour, so that they could be attached to a fuselage assembled from sections made in 4 countries, in a building constructed specifically to hold them. The 4 engines hanging under those wings were designed by engineers at Rolls-Royce to a bypass ratio that made them among the quietest large turbofan engines in service. The fly-by-wire computers sitting between the pilot's inputs and the control surfaces were programmed with envelope protection so that no command from any human could push this aircraft beyond what its structure could manage. The program that produced all of this was launched in December 2000 and cost far more than it recovered. The last aircraft it built was delivered in December 2021. In between, 251 aircraft were completed and flown to airlines on 4 continents. And those aircraft flew more than 800,000 flights without losing a single one. The people asleep in the upper deck right now do not know most of this. They know the seat is flat. They know the cabin is quiet. They know they are less tired than they expected to be. The engineering lives underneath the experience, invisible and continuous, doing its work the way the body does its work during sleep, without being asked to, without stopping, without requiring acknowledgement. That is what the A380 is at its foundation. A very large and very deliberate collection of engineering decisions, accumulated over decades, converging on a cabin that allows 500 people to rest in the sky. If you are somewhere comfortable as this ends, you have something in common with them. The questions that brought you here, the facts that carried you through the night, are settling now. The work is done. The aircraft is still flying somewhere. The wings are still flexing in the dark. If tonight's journey through the A380 is the kind of story you want waiting for you, subscribe to Simple Science so the next one finds you. A like is the quietest way to say good night. And wherever in the world you are watching from, at whatever hour this finds you, sleep well.